In section 3.5, we are going to be looking at limits at infinity. So clearly, infinity is not a number, so we need to define what we're actually talking about when we say limits at infinity. So we're going to say let L be a real number. The statement, the limit as x approaches infinity, that's what we mean by limits at infinity, equals L, means that for each epsilon greater than 0, there exists a capital M greater than 0, such that f of x minus L less than epsilon whenever x is greater than m. I'll draw you pictures, I promise. Just write them down for now, okay? And the statement, the limit as x approaches negative infinity of f of x equals L, means that for every epsilon, or each epsilon greater than 0, there exists a capital N less than 0, such that f of x minus L less than epsilon whenever x is less than n. Okay, a couple more definitions before I get too farther down the hole, okay? Just fill them in. I never ask you definitions for a test. And not only that, but you've seen this kind of a definition before. You guys remember it on exam 1? Epsilon delta stuffs, and we had ones where we proved that certain values worked. That's not what we're doing either. Okay, so hold tight on that. Yeah, it's not something you're going to be asked to replicate, okay? I shouldn't say I never ask you definitions, but I tell you when I'm going to ask them, right? I'm very clear up front. I'm not asking you to memorize this. I won't ask you to memorize this, no. Okay, horizontal asymptote. A horizontal asymptote is the line y equals L is a horizontal asymptote of the graph when as x approaches negative infinity or x approaches infinity, f of x is equal to L. Okay, you've seen horizontal asymptotes way back at this point. I mean, somewhere in the middle of your mathematics in high school. You saw irrational functions in particular, and you saw horizontal asymptotes. Okay, we'll draw more pictures, I promise. One more piece. Limits at infinity. If R is a positive rational number and C is any real number, then the limit as x approaches infinity of C over x to the R is equal to 0. Furthermore, if x to the R is defined when x is less than 0, then the limit as x approaches negative infinity of C over x to the R is equal to 0. Okay. All this one's talking about is that if you divide by something getting infinitely large or infinitely small, it's going to become 0. Now visually, let's talk about a visual on this one because I keep saying I'm going to do it and I haven't done it yet. Visually, what this is actually talking about is related directly to the previous slides. What it's saying is that if you had a graph that looked like this, and this is roughly a graph, I don't know why I drew it in this particular way, but this is actually the graph approximately of negative 1 over x. Okay, that's what it is. Couple of things. First of all, do you see a horizontal asymptote? Do you see one? Okay, so the horizontal asymptote, hopefully, that you're seeing is actually the x-axis, just highlighted in orange, right? It's a horizontal line that you get really close to on the other side, and you could actually touch it, but not at the ends of it. You might cross across it. Like it could actually, it doesn't happen real frequently, but you could actually have a graph that does this. Like that's a possibility to still be a horizontal asymptote. But the end behavior, what's happening on the ends is that you're approaching it and you're not touching it again. Okay, so that's a horizontal asymptote. What this theorem says is that when you have this negative 1 value, and there's nothing special about the fact that it was negative 1. I know it's negative because of the way that I drew the left-hand part above and the right-hand part below. That's why I know it's negative. If I had had a positive, I would just flip this graph upside down. Okay? But the fact that there's a 1 there has 0 relevance. It could be any number on the top, and the graph would look the same. So if I asked you to graph in your calculator 100 over x and 5 over x, the graphs would virtually look the same visually. They'd have the same form, same shape. All this is saying is that if you divide the number, whatever it is on top, by something that's getting infinitely large, right? You divide it by 10, and then by 100, then by 1,000, and by 10,000, then by 1,000,000. Eventually, you're approaching this 0, right? This y value of 0. And the same thing's true if you're on the left-hand side. So if you're dividing by infinitely large negative numbers, negative 10, negative 100, negative 1,000, negative 10,000, eventually it tapers off again at y equals to 0. Okay? We can do it from a number perspective. We've seen that before. Do you remember doing the values in your calculator where we did numerical values? Remember that? Yeah, I mean, so we can do it from a number perspective. That's what this sort of is describing. This slide is more describing what happens from a visual perspective. Hey, what's really going on there is you got a horizontal asymptote, right? And over here, what's talking about is that this value that it's approaching has a constant value. It doesn't have to necessarily be 0. So my whole graph right here that I drew, I could have had it like this, right? I mean, it could be drawn that way. My graph wouldn't exactly be this function. It would be somehow shifted from this. But it could be then that this limit value that you're approaching, I'll draw it dotted, and we'll make it blue. It would be approaching, oh, that's terrible, but give me a second, I'll shift it. It would be approaching this particular dotted line value, and that would be the L that it's referencing back on the first slide. So it doesn't necessarily have to be 0 that's approaching, but it's actually still a horizontal asymptote that's going to be approaching anyway. Okay? So let me show you how it actually works to find these values, because we're not doing this from the perspective of algebra. We're doing this from the perspective of calculus, and so it does look a little bit different. So we're going to take a rational function, which is the function that So we're going to take a polynomial function, f of x equals 5x cubed minus 3x squared plus 10x, and we're going to take that polynomial function and we're going to turn it into a rational function. Okay, so all that this part A is telling you is to take that polynomial that we just were given, 5x cubed minus 3x squared minus 10 plus 10x, divided by x squared. That's the function we're going to be working with, okay? So we're working with a rational function. Everybody good with that so far? Okay, so we've got a rational function. And we're wanting to know what happens to each of these limit values. And there's a couple of different ways that we could do it, okay? So I'm first going to show you one way using a little bit of algebra and then applying that theorem that we had at the very end. And then I'm going to show you another option as well. Okay, so just let me show you the algebra option first because I think that it's the most natural one for what you've seen before. We could actually divide each of these pieces by x squared. So we could write this as 5x cubed divided by x squared, because we did this back when we were doing and talking about derivatives even. And this one over x squared, and then we have 10x over x squared. Okay, is everybody good with the algebra that I just did? Just broke it apart into some pieces. Okay, most of those actually clean up really nicely. What is this 5x cubed over x squared? It's 5x. What is 3x squared over x squared? Minus 3. And what is 10x over x squared? Yeah, it's 10 over x. Okay, everybody good so far? Okay, so as we're taking a look at this, it's wanting us to find the limit. I didn't highlight it at the beginning, but let me go back and do it now. The limit as x approaches infinity of h of x. So I've sort of manipulated it at this point, but I want the limit as x approaches infinity. Of the 5, it's not limit equals. Some of you guys were doing that when we had the first chapter. This is not a limit equals. That's like saying square root of x or square root equals. Square root doesn't equal anything unless you have something underneath it, right? Limit doesn't equal anything unless you have something inside of it. So I want the limit of all of this. So some of these pieces are very easy. What's the limit of negative 3? We've done this before. It's what? Not a derivative of 0, not a derivative of negative 3. The limit of a constant is just the constant. That's what we had back in chapter 1. This is just negative 3. Okay, constants don't change. This piece at the end, according to the last slide over here, what does it equal? Somebody said it. 0. That's right. No, it equals 0. All right. Any constant over something that's approaching infinity, positive or negative infinity, equals 0. So this piece is 0. Now, the kicker is that this piece isn't. What happens if you have the number 5 times something and that something keeps getting bigger? 5 times 10, 5 times 100, 5 times 1,000, 5 times 10,000. It's just getting bigger. Infinitely bigger, right? Yeah, it's approaching infinity. So what happens if I take something infinite and I subtract 3 and I add 0? It's still infinity. right? This is the whole argument of what happens when children say, maybe you've seen even the books before that say, I love you to the moon and back, that kind of stuff, right? They're in more than one book. I have children's books, a couple of children's books in my office and my home that actually talk about it that way. Same thing, that's infinite, the idea of being infinite, right? So I love you to infinity times 2. Okay, well, that's still infinity, right? It didn't get any bigger. It didn't get any smaller. Infinity is infinity. So this limit is actually infinity because I have one piece of it that's infinity. Now, it'd be messy if one of them was infinity and one of them was negative infinity. Then we'd have to talk about what's going on because it doesn't work like numbers, right? 5 and negative 5 is 0. Infinity and negative infinity might not be. But that's not what we have going on this problem. We have an infinity in one piece and the others are numbers, concrete values. They don't have enough value to change anything. So we just have infinity. Now take a look at the same function, but instead of dividing it by x squared, what are we dividing it by? X to the third, right? So let's see what happens differently when that piece changes. Everything else stays the same. So I have the same 5x cubed minus the 3x squared and the 10x. All of that stays the same, but now it's written over x cubed. We're doing the same stuff, right? We're going to take 5x cubed over x cubed, and we're going to take the 3x squared over x cubed, and we're going to take the 10x over x cubed, and we're going to reduce it with some algebra. So 5x cubed over x cubed is 5. 3x squared over x cubed is 3 over x, and it's a negative just for the sake of writing. And then I have 10x over x cubed, and that's 10 over x squared. Everybody good so far? That's algebra. Good, good, good. And then what I want, the calculus part, is the limit part. I want the limit as x goes to infinity of that calculus, the 5 minus 3x plus 10 over x squared. I want the limit of that. So what's the limit of a constant? It's 5, right? Because the constant's 5, so the limit's 5. What's the limit of 3 over x?
0.
That's 0. That's the theorem that we just encountered. And what's the limit of 10 over x squared?
Also 0.
It's also 0, right? So now I have 5 minus 0 plus 0. What do I get?
5.
I get 5. Now let's say that you wanted to confirm this. How could you confirm that your answer should be 5 or your answer should be over here infinity? How could you make sure? How do we often verify what we're doing with what we... Nope, not plugging the original. That's a really good guess to talk about the original because we do a lot of things going back to the original. Looking at a graph. Yeah, the graph's going to be really helpful. If you look at the graph, and it's not the graph of the original function, but it's the graph of the function we created. So like the graph of this, right? Or the graph of this. What you'll see on the first one is if you take the look at this graph, you're going to see a graph that does, oh, I drew it on the other slide, this weird, like, it's called a slant or an oblique asymptote. You don't like them when you encounter them in algebra, but that's what you're going to see happen. It's going to look like it's got this sort of like asymptote, but on a tilt, right? That's going to continue to go up to infinity. But if you look at this one over here, you're going to see that the asymptote's a horizontal asymptote that it's approaching instead at a level of 5. Okay? So that's what this is going to end up looking like if you verify them with your calculator. So let's take a look at 3 more. I think there's 3 more. 3. 2, 3, and 4. Did they start with 2? Yeah. 3 more where we're going to find the limit, same idea. Now, the difference in the what's remaining, well, what we did before, they were all divided just by x, right? But these pieces are divided by something with some addition and subtraction potentially in the denominator, right? So how does that affect things differently? Because I can't just do the algebra to reduce. It doesn't work that nicely. Okay, so it's sort of one of those, like, leading you in nicely into what's going on. But there's some really cool stuff that can work on these too that makes them easy to work with. So what I want you to notice is that the numerator has the biggest power of x is x to the 1, right? Does everybody see that? And the biggest power of x in the denominator is x to the 3rd. So the reality here is that I really basically have negative 2x over 3x cubed. The other pieces are sort of just like fluff. they don't change the value very much. Are you with me? These are the pieces that dominate what's going on. And when I reduce this, I end up getting negative 2 over x, 3x squared, if I were to reduce that. So the overall basic values, like almost like, it's like an approximation, right? So like when you're at the cash register, you're like, I think it's going to cost me about $10. Like, you know, it's not going to be exactly $10, but you're going to be pretty close. This is not exactly negative 2 over 3x squared, but it's pretty close. All right? So if that's the case, what do we do about it next? How do I actually show the pieces that I want to show? That's what I want to show you. But in the end, what's going to happen is I'm going to essentially get the same answer that I get if I were to use the function negative 2 over 3x squared. Okay, so let's show you what happens on this. All right, let me rewrite it actually, so I'll have some more space to space it out. Whatever your biggest exponent is, in this case it's x cubed. Everybody write, it's x cubed. We're going to multiply every term in our rational function on this one by 1 over x cubed. Every piece of it. Okay, that's the same function that I started with, because every piece has been multiplied. Essentially, I've multiplied the entire numerator by 1 over x cubed, the entire denominator by 1 over x cubed, and 1 over x cubed divided by 1 over x cubed is 1. Okay, so I've done the numerator and the denominator by the same value. Some of it simplifies, cleans up, some of it doesn't. The reality is, it kind of doesn't really matter. There's a lot of really nice things that are about to happen. So I've got 3 over x cubed. I've got negative 2 over x squared. What happens to the denominator first piece? It's 3. And then I have minus 1 over x cubed. Okay, is everybody good with where I am at this point? You see the pieces. Here's the beautiful thing, and here's why we did that. Every single piece that's something over x or x squared or x cubed, what's its limit as x goes to infinity? It's 0. All of these are zeros, which means the entire numerator is 0, and the entire denominator here is 3. And what is 0 over 3? 0. This limit's 0. And so every problem ends up looking and feeling just like this. I end up with constants once I do the limit values. But it only works if you multiply by the reciprocal of your highest degree term. Right? It has to be the one. If you multiplied through by 1 over x squared here, you'd end up with some variables still, and things would not work out to being constants everywhere. You'd still have some x's involved, and that wouldn't make it actually simplify and work out. All right. I was supposed to finish through 3.5 today. Clearly, I did not. I'm okay with that. What we will do is we'll do our next 2 examples next time. We'll finish 3.6 next time. We'll push the quiz to Friday. And, oh, that was unfortunate. Hang on just a second. I want to make sure one more thing. Okay. Yeah, so we'll push the quiz to Friday. It'll still be over 3.3 to 3.5. And then we will also do 3.7. We may start it next time, or we may push it into Friday. We'll see. Yes? There's no test this week.
Okay.
No.
There was one for some reason.
Nope, no test this week.
Good.
Nope. Okay, everybody good?
Yep.
Awesome.